Hello everyone. In this session, I would be talking about using decision trees for the classification purposes. We already know that for various kinds of classifications, you can use a KNN algorithm, which is the nearest neighbors, or you could use naive-Bayes algorithm, especially if your classification is more of categorical kind of classification is based on categorical kind of data. KNN algorithm, especially if your data is more and more quantitative in nature or continuous in nature. So the objective is still classification. We are allotting the data to a group. We are allotting a particular example to a group of values. We are classifying it into group 1 or group 2 based on the various features that are associated with that particular example, with that particular case. But the approach that we are using for doing that process is different in all these methods. The same way, even in classification, even in decision trees, the approach that we are using will be different from rest of them. But the objective is still classify the data. It's also a supervised learning process. Classify the data into an appropriate group. So we would be understanding the decision trees, how they are typically different from your nearest neighbors kind of algorithms, or how they are different from naive Bayes and various other classification algorithms. As I have indicated to you earlier also, all these classification algorithms, they do the classification of the data into groups, but the approach that they are following to do the classification is entirely different, and there is no single procedure which says that for this kind of a data, this approach or this algorithm will always give better results compared to this algorithm. So there is no such kind of assurance that is given, which means it is better that I have a good understanding of all the different algorithms, all the possible algorithms for classification of the data. Try applying all of them given a business problem and see which one is best suited for the kind of the data that we have taken up, and based on that use that algorithm for the prediction purposes. So that is what is the typical process I would suggest for any kind of classification problem. Now, just to have a good understanding, this decision trees, they actually do the classification of the data based on a mechanism called divide and conquer. Otherwise, we also call it as recursive partitioning. So we will be understanding what this mechanism is all about. So it is dividing the whole data into different groups, and based on that assigning the group membership to each of the records. And though there are, for doing the same decision tree process, there are many different algorithms that are existing. Different researchers have come out with different kinds of algorithms based on different techniques, but we would be talking about one of the most widely used technique called C5.0 algorithm for creating a decision tree. So we'll see how do we implement this kind of a tree in R and how do I really interpret the data. Then I have to choose the best split. Right now there is a, so that this is like a tree. So probably the tree shape is more like this. So there is a splitting of the data that is occurring across. So I need to know what is the basis for splitting the data. How do I really choose the best split. So I have to have some amount of understanding regarding the same. And now, okay, if the tree gets built like this, if the tree keeps on growing like this, is there a way where I can take a decision where to stop the tree? Should I allow this tree to grow to unlimited length, or should I really look at a mechanism where I can stop the tree from growing? Now that is one essential thing that we need to have an understanding of. So how do I really decide where to prune the tree? And all these things we are taking up with the help of an example. We will try to take a data set. We'll try to build a C 5.0 decision tree algorithm. We'll try to build a model based on that algorithm. Use that model for the prediction purposes and try to evaluate the goodness of the model. Alright. Now, just trying to understand about the decision trees. If at all, let's say I have a task of making a difficult decision, right? I want to make a decision whether a particular person will be, or probably let's say I want to take a decision whether a particular project should be taken up or it should be rejected. Let's say I am a HR guy, I have to take a decision whether a particular person needs to be recruited or rejected. Let's say I have, let's say I am a credit officer. I want to take a decision whether a loan should be given to a particular person or he should be rejected. So these are all different kinds of difficult decisions that I am talking of. In general, when I am presenting, when I am coming across such a kind of a difficult decision, sometimes what option do I need to choose out of these two? I make a list of pros and cons. Okay, if I give a loan to this person, what are the positives? On what basis I should give a loan? Or what are the negatives? Why should I not give a loan? Why should I give a loan to this person? Why should I not give a loan to this person? So I make a list of pros and cons for each possibility. So if I am rejecting a particular person, why should I reject him? Why should not I reject him? So I have a list of pros and cons for each of the possibilities, and based on that, sometimes I take a decision. So in machine learning, we are trying to automate that particular process. So based on various features, even if I have to take this decision manually, I will look at different features. Oh, he is a very young guy. So his age is much lesser. So there is a chance that he is earning more. So he may not default. Or he is a very highly qualified kind of a guy. So he must be earning more. So he will not default. So I am trying to look at different kinds of features which will say he might default or he might not default. And based on that, I am eliminating some of the options. I am shortlisting on some of the options. And based on that, I might end up taking my decision. So that is how, when I am presented with a decision making role and I have to typically take a decision, I would be following such a kind of a process. Now, this is how I have the decisions of predicting. By doing some kind of eliminations, I am reducing them to a small set of choices. But within that small set of choices, all of them are very, very specific. So I am eliminating some kind of features, I am retaining some kind of features. So based on them, finally, I have to make my choice though the number of options that are available to me are narrowed down by doing this process, but within those options, which one do I need to select? Now that when we are doing it in machine learning kind of a way, we are dividing the data into smaller and smaller portions, right? We are doing subsets of the data based on various features. We are taking the subsets of the data, we are dividing the data into smaller and smaller portions. For each of the portion, we are identifying the pattern. Okay, this subset, is it that this kind of subset of people, they need to be rejected because there is a good chance that they will default on the loan, and some other subset of the people, they need to be given a loan because there is a very little chance that they will default. So I am trying to identify the patterns within the different subsets of the data, so that based on that kind of a learning of the pattern, I'll use those patterns for my prediction purpose. So the knowledge that I am gaining through these various subsets, I am putting them in the form of logical structures. Okay, this subset is nothing but age greater than 50 guys and who have taken loan more than 5 million. So probably this is the kind of a simple structure. So a person is having an age of 50 and loan amount of greater than 5 million. That is the subset of these people. And majority of the people within this subset, historically, they have defaulted on the loan. So it's better that I reject the loan for him. So the knowledge that we are gaining based on the various subsets, we are trying to create them in the form of logical structures. So there is no statistics, there is no hypothesis testing, any of these things in the process. We are understanding all the rules, all the logics in terms of simple, greater than, less than, equal to kind of associations itself. Now, in terms of identifying all this process, this all will come under the decision tree process. But within this decision tree, there are n number of methods that are there, and different methods are applying different strategies. So how to create subsets, how to do the partitioning of the data. So because based on the partition itself, we will try to understand the characteristics of this subset. We will try to do an abstraction and generalization of this particular subset so that it can be used for better prediction purposes. So I need to have very much pretty comfortable and useful mechanisms to create the subsets out of the data. So the partitioning of the data is done through various kinds of algorithms. So C50 is also doing one such kind of a subsetting, whereas there are various other kind of algorithms which can solve similar kind of problem. So there are many implementation of the decision trees that are there in R, and even theoretically there are different kinds of implementation of the decision trees, whereas we are focusing more only on C5.0 algorithm. So we really need, if we want to go more and more deeper in terms of decision trees, we need to have a complete read through of various types of decision trees that are possible, and how do we really go ahead implementing all these algorithms for various classification tasks. And let me tell you once again, there is no measure which says universally this particular algorithm is superior to all other algorithms. This has not been proved. If that has been there in place, I would have knocked off all the other algorithms and I could have gone ahead only with the superior of all those algorithms altogether. Now, how do we really get into the understanding of the decision trees? Now, the word itself is clear. The learning is built in the form of a decision tree. So we will get a tree structure as a part of the abstraction process of the model. right? When we are giving a data to the algorithm, so we have chosen an algorithm, we have given the data. The way the decision tree algorithm will learn from this data is it will create a tree structure. So tree structure is not statistical here, series of logical decisions. So greater than something, less than something, equal to something. So they are created in similar to that of a flowchart. And for each node, for each path, there is a decision to be made. So this path of people, whether they would be defaulting on the loan or whether they would not be defaulting on the loan. So the data is broken into different structures, and based on the different structures, based on the different groups that the data is broken down into, I would be making out which set of people would be defaulting and which set of people would not be defaulting by looking at the decisions of each of the subgroups. So the whole data is split into branches, and for each branch I'm looking at the choice whether this particular branch is going to default or it's not going to default. And the whole tree is terminated by the leaf nodes as I have drawn earlier, right? Initially this is the full data. I am breaking it into two different groups. Now this data again I have broken into two groups. Even this data again a subset into two groups. Again this is also created as a subset. This is also broken down into subsets. So the process is continuing like this. The whole data is getting broken down into subsets. Now this is what I am calling as the leaf node. So first the people who are belonging to this put together, is it that they belong to the default category or they belong to the non-default category? They belong to default or no default. So the tree is terminated at the leaf nodes, and I need to give the decisions at the leaf nodes. So the data is beginning at the root node. This is what we are calling as the root node. So it is passing through the various decisions in the tree. So this whole flow is there based on the features. So this could be like age is greater than 50 and age is less than or equal to 50. If the age is greater than 50, the data will come this side. Age less than or equal to 50, the data will come this side. Let's say the debt to income ratio is greater than let's say 10, and this is less than or equal to 10. So if it is greater than 10, it will come here, less than or equal to 10, it will come here. So something like this, the whole breakdown will keep going. And finally, at the node, okay, now someone who is age greater than 50, whose debt to income ratio is greater than 10, so I will have to make, I will see from the historical data, majority of the people who are falling into this particular group, they are defaulting on the loan. So I will make a prediction that this set of people are going to default. So that is how the predictions are typically made by this decision tree algorithm. So the path taken, it funnels each record into a leaf node. So every record will come up to this, either here or here or here or here, and based on it I will have a class that is assigned to it saying whether the person will be defaulting or he or she will not be defaulting. So this is how the decision tree learning algorithm is going to be built. So it is more and more appropriate for applications where the classification mechanism need to be transparent, especially for bank loans. If I am rejecting a loan for a particular person, I have to clearly specify why he has been rejected. So there should be a lot of transparency in the process. When someone is rejected for a job, I should have a mechanism which says why he is rejected. I should be able to explain the stuff. So wherever there is a requirement that I have to give an explanation, where the grouping process is needs to be utmost transparent, Compared to various other mechanisms, I would be relying on the decision trees for the classification purpose, especially when the results need to be shared for the purpose of decision making. So I may use KNN algorithm, I may use naive bias, I may use neural networks, I may use support vector machines, and so many other things for doing the classification job itself. But every model has its own set of limitations also. When I say neural networks, I will not be able to explain the model quite sophisticatedly to the user. Result sharing would be a much difficult aspect there. So, wherever the objective is to share the result, facilitate the decision making more and more comfortably, we would be relying more on the decision tree kind of a process itself. So especially if you see credit scoring models, so when a person is typically rejected a particular application, I should have a very clearly explained mechanism why he is rejected a particular loan application, why his loan application is rejected. Similarly, when I am looking at customer satisfaction, the whole study of the customer satisfaction need to be shared with the management and advertising agencies. So wherever the data sharing is very important, then decision tree is much more appropriate compared to using any other kinds of methods for classification purpose. Similarly, if I want to diagnose the medical condition based on the lab results, symptoms, so I want to diagnose the medical condition. So here also I can use the decision tree because the results need to be shared with the parties when and where required. So in all these cases, compared to the other algorithms which are used for classification purpose, I should rely more and more on decision trees itself. But looking at the limitations of this model, if the data is having too many nominal variables, right, this is the biggest limitation. Whereas your naive bias will work, naive based algorithm will work majorly when there are nominal variables in your data. And few other algorithms also will work more and more comfortably when there are nominal features in the data. But what you typically observe is if your data is having good number of nominal features and each nominal feature is having so many categorical categories, then the tree will become very complex, and in those kind of scenarios I really don't suggest using the decision trees for that purpose. If majority of my variables are quantitative variables, which are like continuous variables, hardly one or two of them are categorical variables, nominal variables, and even those one or two categorical variables, the number of categories within each of those variables is also very limited, then I can very well rely on going ahead with the decision tree kind of models itself. The decision trees use a mechanism called divide and conquer, otherwise called as recursive partitioning. So where the data is typically split into smaller and smaller subsets. So the intention is split the data in such a way that each subset is more and more similar in many aspects. So we are trying to split the whole data into smaller and smaller subsets, and each subset is more or less similar in behavior. And the algorithm which we are talking of, the C 5.0 kind of an algorithm, it will choose out of all these features one particular feature, right, probably age, or let's say the debt to income ratio. So it will look at one such feature which is the most predictive of the target class. Now it is like this. This is the whole data, right? Now the data is partitioned into different groups. So this is how the data is partitioned into small subsets. Now within this particular subset, there are some defaulters, there are some non-defaulters. Now, what the machine learning model, which is the C 5.0 or any decision tree model, what it will do is, okay, there are this is the subset. Now, within this subset of data, there are so many features. Now, which one single feature is able to distinguish between the defaulters and the non-defaulters more significantly, more comfortably? Is it the age which is able to differentiate between defaulters and non-defaulters comfortably? Or is it the debt to income ratio based on which I am able to segregate the group more comfortably? So which feature is the most predictive of the target class? Right? Within this particular subset, which one I can rely on more to classify whether the particular person will default or not? So cases are partitioned into groups of distinct values of this feature. So we are classifying it. So these kind of out of this subset, so this set of people are going to default, this set of people are not going to default. So that is how we are going to have the first set of tree branches. So this algorithm keeps continuing. Okay, now if I am not able to break it down, one more subsetting of this is going to happen. So this is a kind of a divide and conquer. Every node is again broken down until I get the subset in such a way that the majority of the candidates, the majority of the cases that are there in this particular subset are all belonging to the same class. So there are three different kinds of stopping criteria that we generally talk of. So when this is the subclass that is created, almost all the elements of this subclass, subset, they belong to the same class. All the people, all the cases in this particular subset, they are all defaulters. Then I will not divide the data any more further. So this part is left like this. Or there are no more features. All the features I have used to classify people. So I don't have any more features to break down this data. Then also I can stop. Or the tree has already grown to a predefined size limit. So I say let the tree be 4 layers, 5 layers. So I have predefined the size limit, and once it has gone to 3 layers deep or 4 layers deep, I want to cut off the tree. So this is where I can come out with a stopping criteria, and this is where the divide and conquer process is going to stop. Try to understand here in decision trees, the tree can grow to any layer of depth unless I have a explicitly defined stopping criteria. So that because of that reason, what can happen is if I have 500 cases for learning, it can go to such a way that all 500 leaf nodes could be there finally. So the tree can go even to that kind of a depth. I can create 500 leaf nodes out of that 500 cases, which means the learning will be specific to each case. There is no abstraction, there is no generalization. It becomes more and more specific to each case. And because of that reason, there is a good possibility that your model will be overfitted. Right? And because of that reason, the decisions also will be more and more overly specific. So that would be a very big danger when I am using decision trees. There is a good possibility of overfitting if I am growing the tree to a very, very large size. So the model can work very comfortably with the training data, giving very few amount of errors. But if I am trying to test this over a testing data, the model will fail very miserably. So this is one more place where we have to be very careful of when we are using the decision trees for the classification purpose. So because the data can keep on splitting based on all the features. So if I have 8 to 10 features, so based on each of the feature, the data will keep on getting split into subgroups. And because of that reason, it may so happen that each leaf node may contain hardly one or two data, hardly one or two or three cases in each of the leaf node. So it becomes more and more specific, no generalization that is happening. So we have to be very much aware of this, and wherever possible it's better to cut off the tree, prune the tree. So even pruning the tree is an important art in this context. So more and more features are there. If the features are 8, 10 kind of features, the decision tree becomes more and more complex. Too many nodes, too many branches, too many leaves. So even the decision taking also becomes very, very complex decision making process. So we have to be very much aware of the downside of using these processes as well. Now, coming to the specific, as I have already indicated, the decision tree algorithms, there are so many implementations, right? I am planning to have a different course altogether where I would be covering a big wide variety of decision trees alone, different kinds of implementations of the decision trees, right? So you have so many such kind of decision tree algorithms that are there. More and more popular industry standard kind of an algorithm for producing the decision trees is the C5.0 algorithm. Few important advantages and disadvantages that we need to be aware of with respect to these algorithm. One, it's very easy to understand. Once we take up an example, you will be realizing that deploying this algorithm is very, very easy. And few important advantages, it's an all-purpose classifier. When I say all-purpose classifier, almost all the problems can be handled through this C5.0. So there could be, my data could be having a lot of numerical values, or it could be having a lot of categorical values, or there could be some missing elements also in the data. If you try to remember your KNN algorithm, nearest neighbors algorithm, it will not work if there are nominal variables at all in your data. So you have to convert them into dummy variables. It will not work if there are missing values in your data. So you have to handle them. Whereas when it comes to the C5.0 algorithm, it works. Even if there are nominal features in your data, even if there are missing data, so there is an automated learning process. All kinds of data can be very well learned without too much of modifications to the data. So that's the reason we are calling it as an all-purpose classifier. It's not that I can use this only when my data is numeric or only when my data is having a majority of nominal variables. But of course, just like any other decision tree algorithm, the model will become very, very complex if there are too many nominal variables, and each nominal variable is again having a high number of categories. The model will become very, very complex, so the interpretation will become very difficult. But that is not the problem of C5.0. It is in general associated with the decision trees. And there is some basic decision making criteria there. So even if you are giving all 10 features to it for each record, it may use only 6 of them or 7 of them. Only the most important features will be used, which are really helping in terms of classification. But any feature that is not helping in terms of classification, it will not even use those features as well. So that's one more goodness associated with this decision tree algorithm, and can be used on data where even the training data is very, very small, or it could be very, very large. So the size of the training data really does not matter. Even if the training data is very large or even if it is very small, I can comfortably use this C5.0 algorithm. And The other major advantage is I really don't need to have a mathematical or statistical background to interpret this output of this algorithm. There is no mathematical or statistical terms, no hypothesis test, no p-values. If I have to interpret this C5.0 algorithm, everything is explained in, you can explain it in plain English by looking at the output of the C5.0 algorithm. So what you will typically find is compared to various other complex models, it is much efficient. But of course, having looked at the positives, we should also have a good understanding of its negatives also, so that we are more and more informed and aware of the process. So they are more and more biased towards the split on the features. So if there are too many nominal variables and each nominal variable is having many categories, what we typically see is they try to give more importance to that particular variable compared to other variables. If there are too many nominal variables and each nominal variable is having a high number of categories, what we observe is the decision tree models try to split the data first based on those categories itself. Now that is where more and more biasing comes up, which we have to be very aware of, and that's the reason I was saying if there are too many nominal variables in your data, try avoiding the decision tree algorithms per se. Not just about C5.0. In general, decision tree algorithms, you can keep them at bay. Then, there is a good possibility of overfitting or underfitting the model. Any decision tree algorithm will have this weakness. There is a good chance that I either overfit the model or underfit the model. Right? So we have to be very careful from that dimension. And I have a trouble in terms of modeling some relationships. If there is a lot of correlation between the variables, if there is a lot of interdependency between the variables, the splitting, if the variables are very independent, then the splitting is quite comfortable. But if you see, if the variables are very interrelated, which means the correlation between the variables is much higher, then I would see some kind of a problem in terms of the classification of the data. So I have to really see what is the extent of correlation that is existing between my variables before I go ahead using a C5.0 decision tree algorithm. Now, if the training data is changed a little bit, see, remember here there is no statistical model or a formula that is getting built. So if my training data changes a little bit, even my logic will change. So it's not just the small formula changing, the whole logic may change drastically. Probably instead of some five records x1 to x5, I replace them with another 5 records y1 to y5. Then there is a good chance that my overall logic will change drastically. Right, earlier a feature A was given the first important, now the feature B might come out as the first important. So the overall logic also might get changed quite drastically. So we have to be very careful, we have to be looking at all different possibilities before we go ahead in terms of using this algorithm for the production data. And if the tree size is very large, the interpretation is very difficult, and whatever the decision that I am making may be more and more counterintuitive kind of a decision. So I have to be aware of the limitations. Though it's a very good model to use, I have to be very much aware of the limitations that are associated with the model as well. Right? Now that we have a good understanding about this C5.0 decision tree algorithm, we also need to know what is the way that the splitting actually happens on the data. We said this algorithm will split the data based on the various features, right? Now, the first most important challenge in terms of splitting is which feature do I need to split up, right? Should it split on the age of the person, or should it split on the amount of loan that he has taken, or should it split on the gender? So what is the split that really need to be? What is the feature on which the splitting really needs to happen? Now, if if the segments of the data, whatever is the splitting that it is doing, if this segment that is being taken, let's say it is trying to do the split based on the age. So let's say it has come out with below 40 and greater than or equal to 40. Now if it comes out that people, all of them who are below 40, they did not default, then this is called as a pure split. This is a pure segment. Whereas when you are talking about greater than or equal to 40, let's say 80% of them are not defaulted, but 20% of them are defaulted, then this is not a pure split. So after the segmentation is being done, if the segment contains only a single class, then we are calling it as a pure segment. Now I have to measure the purity of the segment. There are different ways to measure the purity, out of which one mechanism that is even being engaged by the C5.0 algorithm is entropy. Entropy tries to understand how mixed the class values are. As I said here, this particular class contains 80% non-defaulters and 20% are defaulters. So it is trying to understand how mixed the class values are. That's a measure of the mixture of the class is being measured through entropy. If the minimum value is 0, then the entire sample is pure. The split is pure. Means it is completely a homogeneous class. All the values in that class are very much homogeneous, which is like 100% of them belong to the same group, either no default or default kind of a group. One indicates maximum disorder. So 100% of the values are completely, heterogeneous kind of values. And the way we measure the entropy here is through this formula, where I am looking at C different classes. If the data is split into C different classes, I am measuring the entropy as minus Pi. Pi is the proportion of the values falling into the class I. So the proportion of the values, so here we said 80% of the values fall into non-default category, whereas 20% of the values fall into default category. So the entropy will become minus 0.8 log 0.8 base 2 plus minus 0.2 log 0.2 base 2. So this will become the entropy, because the proportion of the values falling into that segment, in each of them, proportion of the values falling into the class I will give you the entropy of that particular class. So when we are talking about any particular data, any particular classification, we will look at what is the proportion of the values that are falling into the target class versus proportion of values falling into the other target class. So based on that, we are trying to compute the entropy. So for all the possible two class arrangements, we can look at computing the entropy. And if required, I can even create for all different possible values, right? If the p-value is this much, or if the p-value is something else, I can very well compute the entropies for all possible values, create a kind of a graph, and finally see where the entropy is much higher or where the entropy is much lower. So if one class is dominating the other, as I said, if all 100% of them are belonging to one single group, either the no default or the fully default kind of a group, we see that the entropy will come to close to zero. So if one class is fully dominating the other, then the entropy will come more and more closer to zero. So this is where the system would be finalizing on. It will try to see in which class splitting the entropy is coming more and more closer to zero. That kind of a class splitting is what is typically preferred by the model. So that is how the entropy is computed, and based on the entropy for each splitting of the class, that particular feature which is resulting in a very less value of entropy would be typically considered by the model for the splitting purpose. Now in this context, it's also important that we understand another important definition called information gain. So C5.0 algorithm here, it is using the entropy to calculate by how much extent there is a change in the homogeneity of the group. Because of this split, how much homogeneous this particular group is becoming, and how much, what is the proportion of the decision variable in this particular group. So I have to really look at what was the entropy before the split, what is the entropy after the split based on a particular feature, by how much extent the entropy got reduced. That would be the base. So whichever is, that is what we are calling as information gain. By how much extent the entropy is coming more and more closer to zero because of this particular split. So if the entropy is reduced quite drastically, then that feature would be very much used for splitting the data. But if the entropy is not changing much, it means that the information gain is very limited. So I really don't need to consider that feature for the splitting the data purpose. So the total entropy because of any split is nothing but the sum of the entropy of each of the partitions multiplied by the weight of that particular partition. So it's a kind of a weighted average. So the entropy after the split is nothing but weighted average of the individual entropies of each of the partition. So the one which has resulted in a much reduced form of entropy would be the choice for the selection of the feature for the splitting purpose. So the information gain, higher is the information gain. So if the information gain is high, means the entropy has reduced quite drastically. So entropy is earlier, let's say if it was 0.9, now after the split it became 0.6. So there is a big reduction in the entropy. The information gain is to the extent of 0.3. So for this particular feature, if I am splitting on this particular feature, the entropy has come down like this. So this would be a better feature to create a homogeneous group after the split. So if at all I am talking about a maximum information gain, it's like entropy falling to zero. So the maximum information gain is in this case 0.9. It is equal to the entropy prior to the split, because post the split we are expecting the entropy to become zero. Then only there is a possibility of maximum entropy, maximum information gain in the process. And when such a thing is happening, the whole group is homogeneous. So the decision making is quite simple for that particular group. So the decision tree is using the information gain as a criteria for splitting all the variables, whether it is a categorical variable or even a numerical variable. In case of numerical variable, it will try to put, okay, greater than 30 versus less than or equal to 30. So the groups are actually created, two groups, binary groups are created based on a threshold value. So greater than or equal to threshold is one group, less than or less than a threshold is another group or something like that. So the overall numerical variable is also reduced into a two-level categorical feature, and based on that the information gain is computed. And wherever the information gain is much higher, that feature will be used for splitting purpose. So that particular numerical threshold that is yielding again the largest information gain, should I have to put it as greater than 30 and less than or equal to 30, or is it 40 and less than or equal to 40? Which out of these two, or even is it 25 and less than or equal to 25? So which out of these all possible combinations is giving me a highest information gain? A reduced value of entropy or the highest information gain? So based on that, the decision tree is typically using the information gain to choose what is the basis of splitting the data. Right? So we have to be very much aware, because we need to know how this algorithm is typically doing the overall process. Now here it is the entropy or the information gain that is being used. That is one criteria for splitting the tree, whereas there are several other criteria which are used by other algorithms for doing the same splitting purpose. So we have something called Gini index, where when we discuss about the tree algorithm at a later point, not in this course, but when we look at the tree algorithm, or if you want to refer to a simple tree algorithm in a tree package, it uses the Gini index as a base for splitting the tree. In some cases, I can use chi-square statistic, which talk about the observed versus the expected, right? So, which would maximize the observed versus the expected proportions in the groups. So, based on that, again, the splitting can be done. And even there are some other techniques like gain ratio. Again, different algorithms, they are using different kinds of techniques to really classify the data, to really split the data, so that it can be used for decision tree purpose. Alright. Then the tree can grow to any kind of a size now. So as long as all the cases, all the examples are perfectly classified, until that stage, the tree can keep growing indefinitely. So it can so happen that the leaf nodes will typically contain only one or two or three cases, which will make it more and more overfitted. So the decision trees will have this kind of a drawback, as we have already discussed. So if the tree size is growing more and more large, I can really understand that there could be a lot of overfitting to the data. So because of which I really need to have a mechanism to prune the tree. So pruning is nothing but I am doing a cut to the tree. So I am reducing the size of the tree. Okay, after 3 levels, don't do any more subsets. Stop at 3 levels, stop at 4 levels. So we are pruning the size of the tree, so that the generalization becomes more and more proper. If it is going to a 20 level tree, everything is becoming more and more specific. The generalization will become very vague and absurd. So that is where we are talking of, let's prune the tree after 3, 4, 5 levels, so that the generalization happens more and more comfortably. So one of the solutions is prune. Stop the tree from growing after, let's say, 3 levels or 4 levels. After a certain number of decisions are reached, after 3 or 4 levels, number of nodes, let's say if the number of nodes come to 8 or 10 overall, stop the tree from further growing. So that is what we are calling as a pre-pruning. Before the tree gets built itself, we are doing the pruning process. So here the drawback is we will really not be able to know, by doing this kind of a split, whether some important information will be missed by the tree. Some important patterns would not be understood by the tree because the size of the tree is very, very small. So that point we would be completely missing out if we are doing a pre-pruning of the tree. So in some other cases I would be talking of a post-pruning. Means initially I will allow it to grow to whatever size, free size, almost the full size I will allow it to grow. Then I use different pruning criteria based on the error rate. Based on how much error in terms of classification is coming out. Based on that, I will take a call. Should I cut it after 3 layers, 4 layers, 5 layers, after how many levels I should typically cut the tree. So that could be a kind of a decision I can take after I allow it to grow to full size, looking at the error rates of classification across each of the levels. I'll take a decision in terms of what should be an optimal size for this particular tree. So this is much more optimal. Without growing the tree, I cannot know what should be an appropriate depth for the tree. So once it grows to full size, I will also have all the kind of information with me to see where it is appropriate to generalize the tree, where it is appropriate to cut the tree and allow it from further growing. That is in general for a decision tree. But when I am looking at C5.0 in specific, many of the decisions are taken automatically. So the tree size is also typically taken based on a default. So what it simply does is it grows a full tree initially, then it starts pruning the nodes. If they have very little effect on the classification errors, then it starts pruning it internally itself. So it has a pruning algorithm, pruning logic that is built into it. So initially a full tree is grown, but after that, if that particular tree does not contribute, if that particular branch does not contribute much to the classification error reduction, then automatically the tree is pruned to that level. So there is a subtree raising that happens. Entire branch is moved further up, right? Because some part of the tree is directly knocked off. So the whole entire branches are moved up further up in the tree. And even the subtree could be completely replaced. Instead of having the whole tree structure, everything could be replaced by a simple decision. Even that is taken care of within the C5.0 algorithm. So we have different pruning options. So it will typically try different kinds of pruning options to see if it improves the performance on the test data. I can actually have some kind of in a typical decision tree model, I should be able to explore different kinds of pruning options, and based on that I should see whether the performance of the model is improving or not. So this is the conceptual part of it. Having got a good amount of idea regarding how to work with decision trees, then the next part is really take a data set, try implementing the model, try working out with the different aspects of the model, and see if we are able to do the classification of the data much better, right? Now let's get started with an example where our objective is to model the defaults associated with the loans. Now, the reason typically what we see nowadays is when we talk about the banks, one of the major applications, they are tightening their lending system. So the loans that they are giving to the customers, the procedure for issuing the loans has changed over the period, especially after the financial crisis across the world. The banks have typically changed their lending criteria. So instead of relying on some very common theoretical ways of theoretical factors, theoretical assessments of doing a lending, they are more and more turning towards the machine learning algorithms to identify which customers would be risky customers to give loans, which customers have a high chance of default, and which customers can typically repay the loans quite comfortably. So there is a heavy usage of decision trees, because again, if someone is rejected, I should clearly explain him why he is typically rejected for a particular loan. So because of that explanatory requirement, to do the classification task, decision trees are very widely used. One, they are very highly accurate, and at the same time, I really don't need a mathematical or a statistical background to explain the decision tree to a common person. And even it can be understood quite easily. It can be explained as a reason for rejecting a particular loan. So because of those reasons, decision trees are much more popular in the banking industry. So to get started, first I will get the data. I have a data with me, which I will be loading it into R. Right, I will show you the data. We'll load it into R. I have to identify the decision variable, otherwise called as a class variable. So I would be using the default variable, which will have values of yes or no. It's a decision variable or a class variable. Along with that, I have to identify the factors that are impacting the decision variable. So I would be reading the data into R. So let me do that process. So my data is present as a part of this data sets. I'm calling it as credit.csv data. So I have read it into a file called credit. Now, if I quickly look at the data, I'll take the structure of the data. I'll look at structure of credit, which is giving me that there are 17 variables altogether. 1000 observations are there. But out of this, if I see checking balance, it's a factor variable. Credit history, it's a factor variable. Purpose, factor variable with 6 levels. Savings balance, factor variable with 5 levels. Employment duration, factor variable with 5 levels. Right, and probably other credits, factor with 3 levels. Housing, factor with 3 levels. Job, factor with 4 levels. Phone, factor with 2 levels. So there are so many numerical variables that are used. Now default is my class variable. So I have identified default is no or else. This is what I am calling it as my class variable. So I can very well look at using all the integers and numeric variables. But just for the understanding, I want to use only one or two factor variables for the classification purpose. So that's where I'll create a new variable called credit underscore new. So I'll take a subset of credit, right, where I'll take all the rows, but columns wise I'll take only a subset of them. Checking balance, let me not take. So I'll take the numerical columns first. Month, loan duration I'll take. Credit history, let me take it. It's a categorical variable, but let me take that one because we are talking of default, no default. Purpose, let me not take. Amount, let me take it. Saving balance, no. Employment duration, let me take as 1. Right, let me take the employment duration of the person also. So let me take the 7th column here. Percentage of income, anyhow it's a numerical variable, so let me consider it. Years at the current residence, it's a integer variable, so let me consider that as well. Age also, let me consider it. Other credits, let me leave. Just for the sake of reducing the numeric categorical variables, I am doing this. Housing, own versus rental, let me not consider it. Existing loans, let me take this because it's anyhow it's a numerical variable. Job, let me take the job part. Another numerical variable I am taking, another categorical variable. Dependents also let me take, phone let me not take, and finally the default, which is my class variable, let me take. So I am taking a subset of those variables so that I can build a model slightly better. So I am looking at the credit new as the data with which I would be working. So let me explore this data. So to explore it, it's better that I look at the summary of each of them. So I'll take the summary of credit underscore new. So the month loan duration, there is a minimum of 4, maximum of 72 months, which is 6 years loan, right? So the median is around 18, mean is around 20, the first quartile is around 1 year, second, third quartile is around 2 years. Credit history, there are 293 people who have a critical credit history, 530 of them have a good credit history, some of them have perfect, poor and very good. Amount wise, the loan amount, the minimum loan amount is 250, the maximum is 18,000. Employment duration, yes, we see 62 of them are unemployed in this. 172 of them are having a less than 1 year experience, whereas 253 of them have more than 7 years experience. More or less the data is decently split across all the groups. The percentage of income, minimum is 1%, maximum is 4%. So that's the way the loan has been taken. Years at the current residence, again the same, minimum is 1 year, maximum is 4 years. So we are looking at these kind of people for the model. Age wise, we have people as young as 19 years to as old as 75 years. The existing loans 1 to 4, again different people having different number of existing loans. When we are talking about the job, we have almost 630 people in a skilled job, 148 in a management job, 200 in an unskilled job, only 22 of them are unemployed. Dependents wise, we see anywhere between 1 and 2, 1 or 2. So out of the total data, 700 of them did not default, 300 of them have defaulted, which is more like a 30% default rate. So even if I'm able to create a model which can reduce this default rate from 30% to 20%, even that would be a good achievement for me. So I really want to see if I can really make some kind of a difference. So we got for different kinds of groups, we did summaries, we got some basic idea in terms of how many are belonging to each of the groups. So we have looked at the summaries of all the variables. This is one more step that we need to do. Now, this one is a non-parametric kind of a model. So it does not assume any kind of a distribution of the data. So I really don't need to check whether all my variables are normal or are there some kind of outliers in my data, all that stuff. So these kind of checks are very much required if your data is, if your model is more and more parametric. So just like a nearest neighbors kind of a model, even this model does not really require the outliers to be understood. So this is where I can really take those outliers out. I don't need to consider those outliers and adjusting the data for outliers and all that stuff. So that's the reason those steps are skipped out here. Then we are doing a data preparation here. So we have to create a training data and a testing data. Typically 70% of the total data, which is out of 1000, I'll take 700 records as training data, and approximately 30%, which is 300 records, I'll take as my testing data. So I'll do a 70-30 kind of a random split. So for that, let me initially set a seed so that the same data can be used again and again for different models as well wherever required. So I am setting a seed as 1000. With this seed of 1000, I am creating a train as a variable which will randomly pick out some 700 values out of the 1000. Right? So for that I am using a sample function where I am saying from the chits numbered 1 to 1000, pull some 700 of them, which is 70%, where replace equal to false, which means don't repeat the number again and again. So each number should come only once in the overall sample. So the train is coming out to be this one. If you quickly look at what is contained in the train, these are the numbers. So my first record is 328, then the second one is 759, the third one is 114, and so on. So this is how my records are typically being pulled out from the sample. So overall 700 random values are being 700 values are being chosen between 1 to 1000. So the remaining 300 rows I would be using as testing data. These 700 rows I will be using as training data. So this is where let me use training data. I'll call it as training data, wherein I am taking a subset of my credit underscore new. I am taking a subset where I'll take only these rows. So that's where I'm saying my rows are trained. I'll take all the column. So this would become my training data. And if I'm talking about my testing data, again it's a subset of credit underscore new, wherein I'm taking minus train data. Means I'm taking those rows which are not there as a part of the train. So that would become my testing data. So I have created the training data as well as the testing data. I have split the data into 70%, 30%, and based on that I am able to split the training data and testing data. So there are 70% of the data which are there as a part of the training, 30% of the data which is there as a part of the testing. So probably I can really see, I can create a table now. So here I am assessing the proportion of the decision variables in the training data and the testing data. Okay, overall we have found that 700 people did not default and 300 people have defaulted. So overall it is like 30% of the population have defaulted on the loan. But I want to see that proportion within the training data as well as in the testing data. So if I look at in one of them, I can make out in the other. So I will take, let's say, testing data dollar default. I'll make a table of this. In testing data we have 300 observations. Out of that 300 I could see 90 of them have defaulted and 210 of them have not defaulted. So here also it is like 30% of the testing data has defaulted and 70% of the testing data did not default. So fair enough. So even here the proportion is more or less similar. Okay, so this step is also over. Now I will move to my next step, where I will train my data. I'll train this C 5.0 algorithm on my data. And the C 5.0 algorithm is present as a part of C50 package. So if you don't have it, you install it, whereas I already have it, so I am simply loading the C50. Okay, the C50 algorithm is loaded. So this is the C50 package. Within that, C 5.0 is the name of the algorithm that we are going to use for creating our decision tree. Now C 5.0 as an algorithm, it gives many ways to customize the model. If you look at the typical syntax, right, the best way to look at the syntax is always give C 5.0 with a question mark. Let me see how this help file is giving. Now you could see the intention of this help file is it fits classification tree models. So the whole algorithm, it is fitting a classification tree models or rule based models using Quinlan C 5.0 algorithm. So that's the kind of theoretical algorithm that has been designed. So for that there is an R implementation that has been done and I am directly using that for my business data. So if you see the way it is being done, C 5.0, where I am giving X and Y values. X is a data frame of predictors. Y is a factor with 2 or more levels. I have to give both of them. The number of trials, it's an integer specifying the number of boosting iteration. The same process, how many times with how many different sets of 700 needs to be performed. Because the more is the number of sets with which it will perform, there is a good chance of high accuracy coming into the process for the classification. So if I am not setting the value, the default it would be 1. So there is no boosting that is going to occur out there. So if the value is 1, it indicates that we are using only one model. But otherwise I can make it 10, 15, 20 so that 20 different models can be used, and based on them that classification decision can very well be chosen. And if it is a rule based model, I can very well set the rules. If the rules have to be decomposed, if the whole a tree be broken down into a set of rules, then I'll set rules equal to true. Otherwise, if I'm going to build a tree itself, I can set it as false. Then weights. So for different, by default what happens is all the rows, all the records that we are taking, all the cases that we are considering, they will have equal weights itself. But if I really want different weights for different kinds of data while doing the splitting, then I can very well specify the weights as well. Then the control, if I have to control the parameters, different kinds of control parameters I can set. So which I can see from C 5.0 control. If I want to do some kind of control parameters, so all these things I should set. Either I set a subset, more commonly used ones. If you are looking at the bands, the model orders the rules by their effect on the error rate and groups the rules into specified number of bands. So we won't use that also. Some of the things that we can generally set, no global pruning equal to false. A logical variable of to toggle whether the final global pruning steps to. So I should I set the pruning to true or false? If I am setting it to true, then it will typically do the pruning of the tree. So by default it will not do any kind of a pruning because it is set to false. But when I say no global pruning equal to true, so it would typically do the pruning. Oh, no global pruning is false. So it is doing the pruning in the beginning by default. So if it should not do the pruning, I will set it to true. So by default, it will do the pruning. Then a few other things, I can set the minimum number of cases. In each leaf node, what should be the minimum number of cases that should lie? The default is it will go until there are at least there should be at least two leaf node, two cases, two records in each of the leaf node. One record cannot be there. But if I say no, let it be a minimum of 10, then I have to set it as a part of the control parameters. So these are some of the important things that I can very well set. Early stopping, a logic to toggle whether the internal method for stopping boosting should be used. So should I give an early stopping? By default, yes, it's already set to true. So the default one already stops wherever one of those three criteria, when all the variables belong to the same class, or if there are no more features based on which the tree can be split. When any of these things has already occurred, it will automatically stop the pruning of the tree. That's one of the prime reasons we use C 5.0 algorithm more compared to other decision tree algorithms, because there are a lot of things which are pre-built, which are automatically taken care of by the particular model itself. So if required, I can even give the costs. Another important aspect here. Cost is sometimes we may find some errors are more costly compared to the other. Right? Probably if I make a decision that the person will not default, but he has already he has actually defaulted. This is a very costly error because I am going to lose heavily because of this decision. I have predicted that he will not default, but in reality he has defaulted. So whatever the loan that I have given to him, I have lost that money. Whereas on the other side, if I have decided my decision that was predicted was uh, he will default, but in fact he did not default. I could see I would not have given the loan to him. So here the loss for me is I have lost a customer. Now I need to know what is the cost of acquiring a new customer. So it might very well be possible that this error is very costly compared to this error. Right? I have predicted wrongly, because of which I have lost the money because the person has defaulted, though I have predicted that he will not default. Whereas on the other side, I have lost a customer because I have predicted that he will default, but in reality, he did not default. So I may have to do some kind of balancing between the two. So depending on which error is more expensive, I may assign the cost to different errors, and based on that I can get the model modified as well. So this is how I do the modeling process, training part, and the output of the training part is a model. Once I get a model, which is a C5.0 model, I can very well do the prediction of the data. So that is where I'll use my test data. I'll use the model that I have created. I'll use the test data, and I will try to predict two things. If I type in class here, it will try to classify all the test data into a default or a not default kind of a category. Whereas if I give the input as prob instead of class, it will give me what is the probability that he will belong to a default class and what is the probability that a person will belong to a no default class. So it will give me these numbers in terms of probabilities. Whereas if I set it to class, it will give me the decision variable, whether he belongs to the default or a no default kind of a class. So I can very well get, if I really want to know what is the tree all about, I can get the basic data of the tree. I type the name of the model. So once I type the name of the model, I'll get the number of predictors that have been used, number of samples that are used, what is the size of the tree, average size of the tree. All those typical things are being provided as a part of this typing the name of the model. And if I am looking at the summary of the model, it will give me the complete set of decisions that the model has taken. The way the tree got classified is typically understood through this summary of the model. I put a summary function on the model, I'll get a clarity in terms of what is the way the tree has completely broken down. Then a few more steps. Now let's go to that level, right? That's a better way, so that we'll get started. So I have a training data, I have a testing data, so let me go back. Let me start the model 1, where I'll use the C5.0 algorithm. So C5.0 is the name of the function here. The first input I have to give to it is my training data. But remember, I should give my training data without of only the predictors. It should not contain the decision variable. So I should include all the rows, all the columns except the default column. So if you see how many columns are there, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11th column is my default column. So I'll set it as minus 11. So from the training data, I am taking all the columns except the 11th column. So that is what is my first input, which is the training data. The class is my 11th column itself, right? So it should be a vector, so I can directly take it as training data dollar whatever is the vector default. So that is my class of the training data. Number of trials. If I really want the model to be repeated 5 times, 10 times, so let me put trials equal to 25. So it will be executing the same thing 25 times with different sets of classifications, and based on the number of trials, the classification based on every time with a new different set of process. So based on that, the final classification of the predicted class will happen on the vote of majority. So this is the kind of a boosting algorithm where the random numbers that we have chosen, the 700 values that we have chosen, will not bias the decision process overall. So this is where I can very well go ahead in terms of in terms of repeating the same experiment 25 times. Right now, let me not take any kind of cost, right? But once I let me do it with the base model, then we will improvise the model by putting in the costs also into the model. So let it do the first model. So this is how the model got created for us. Then I can check what the model was all about by typing in model 1, the name of that model. Now you could see, so this is the inputs that you have given, right? These are your set of predictors. This is your class variable, and you have executed it as 25 trials. So there are 700 samples, 10 predictors, 25 boosting iterations you are performing, and it so came out that the size of the tree, average size of the tree, is around 25 records. Okay, so there are some attributes that there are some attempts that the attributes are grouped. So let's see the summary of the model altogether to really understand what the split is all about. So you can look at it that it has done 10 different iterations, so it has done 25 different trials. So your whole output has come out as 25 trials. So let's look at one trial here. Trial 0, the first one. So credit history. Is it perfect or very good? The split has happened in this way. So there are, first thing is it has taken the credit history. We have already said in the beginning, if there are categorical variables, somehow the model gets very biased by choosing the categorical variables to begin with. That is what is the limitation of the decision tree model. But of course, here also you could see the first factor that it has considered is credit history. So either perfect or very good. Then it has said the default is S. So 64 of them are falling into it, out of which 24 of them are having a problem. Similarly, credit history, if it is either critical or good or poor, then it has broken down into two other classes. The month's loan duration, is it less than or equal to 11? Then the decision is coming out as no. So wherein 115 of them are getting classified, out of which 13 of them are errors. 115 of them are getting classified into that group, 13 of them are errors. Whereas when it has gone to month loan duration greater than 11, then again the check has been done, employment duration, is it greater than 7 years or 4 to 7 years. And again within that group we have seen another classification. The month loan duration is less than 33 months, and the amount borrowed is less than 1225, dependence is less than or equal to 1. It has gone to that kind of a breakdown of the tree by using the various variables. So the tree got broken down to this extent in your first trial. Whereas in your second trial, you see there is a slightly different way of categorization that came. The first step, critical. Credit history is critical. We are saying no. So 196.1 and 48 out of them 48.9 are coming out into. So the same process is repeated again and again. So there is a proportion that is being considered. So that's the reason you will find. So here that's the reason we are getting things in the decimals out here, because of the repeated process that is happening. So you could see trial 1. This is how it has gone ahead. The decision tree. In trial 2, you could see that the month loan duration has been considered greater than 33, and from there the whole proceeding has happened. Then in the next one, you could see the month loan duration less than or equal to 11, and the process has continued. So you will find different kinds of ways in which the tree has gone forward in terms of execution. Subset of the variables have been considered, and based on that the tree got built. So that is how the trees get built when you are doing a boosting. It will not take all the variables. It will take only a subset of the variables, and based on the subset of the variables the overall tree gets built. Now if you see here in the 0th trial, 37 is the size of the tree and 128 errors have been created. In trial 1, the size of the tree is only 13, but means there are only 13 different leaf nodes that have worked out, and 173 errors have cropped up in the process. So the overall boost, it looks like 70 errors coming up because of this overall 25 different trials that are executed, and after that the boosting being performed, we see that only 70 errors are overall there, which is more or less equal to 10% of the errors. Now you could see here, this is the misclassification rate. 11 of them. So if you see here, 479, 151. So your model has predicted for this 479 guys, your model has predicted that they will not default, and in reality also they did not default. So the 479 are very correctly classified. Similarly, if you look at this 159, 151, your model has predicted that they will default, and in reality also they did default. So 151 of them are also correctly classified. So overall I could see that 630 out of 700 are correctly classified, which is a 90% accuracy. Remember, this is from the training data, not from the testing data. This is associated with the training data. Similarly, you could see that your model has predicted 11 of them will not default, but they have actually defaulted. 59 of them will not default, will default, but in reality they did not default. So your error rate when you are looking at on your training data, the error rate when you are applying the same model on your training data, the error rate is 70 out of 700, which is 10%. So this is the error rate. And if you are looking at the attributes being used, yes, month loan duration is a very important attribute. Credit history is a very important attribute. The amount that has been taken for loan, the amount that you have taken as a loan, employment duration, percentage of income. So they are all very heavily used across all of them. So the importance wise, these 5 are very important variables in terms of the decision, and gradually the importance is coming down. Job is also the next important. Existing loans that the person is having, the age of the person, the number of dependents he or she has, and finally the years at the residence. So the 10 variables are used in this kind of proportion to finally arrive at this final confusion matrix associated with the training model. So it is not based on the testing model, it is purely based on the training model itself. So as we already know that there is a good chance that the model can do a lot of overfitting. So the 90% accuracy here looks very genuine and appropriate and good kind of model, but I have to really rely on it only after I test it on my testing data. So this is where I will create my testing data. So I'll create P1 as the name of the model or the prediction. For that I use a formula called predict, wherein I'll use my model. I'll use my model as model 1. My testing data again is testing data, all the rows minus the 11th column, all columns except the 11th column, and the type, let me take it as class. So I'll do the prediction through this mechanism. So my model is predicted. Look at P1. So P1 has done this kind of a classification. All these people in the test data are classified as no. These people are classified as S. S, no, no, S, S. So there are some set of people who are classified as no. Some set of people are classified as S. So after doing the learning from the model and using this created model for the prediction purpose, so this is how the classification of the customers has been done on the testing data. So we have done, the training model is already done, right? Okay. So here the number in the parenthesis indicates number of examples meeting the criteria for the decision. So if I go back, I have already explained that. So if you look at this one, employment duration, let's look at the first one itself. Right, if I look at this one, 64/24, credit history perfect or very good. So the number in the parenthesis indicate the number of examples meeting the criteria for the decision. So there are 64 who are meeting the criteria for this S, and number incorrectly classified for the decision. So 24 of them are wrongly classified, 64 of them are correctly classified. So this is how we have to interpret this report that has typically come up. And finally I am looking at the confusion matrix. Yes, so this is what is my confusion matrix on the training data. This is the confusion matrix on the training data. So I am looking at, it's a cross tabulation that is indicating the model's incorrectly classified records. So one, I have true positives, S and S are true positives. Then true negative. So true negative, you have predicted as S, you have predicted as no, and it is S. Then we also have false positives and true negative, true negative is this one. So both of them are no's, so which is true negative. Then false positive, you have predicted as positive yes, but in reality it is no, that's a false positive. Then true negative, false negative, you have predicted as no, but it has turned out to be yes. So these are the 4 different things that are typically coming out. And when so that 4 things I have to see which ones are very costly, which errors are more, which errors are lesser, so that I can even bring in the costs at a later point as a part of the improvisation of the model. So as we have already understood, the decision trees have a very high tendency to overfit the model to the training data. So whatever the 10% error that we have got on the training data, may be overly optimistic, right? We are getting the accuracy as 90%. There is a good chance that this accuracy could be very, very highly optimistic. So it's better that I do this testing on the test data so that I get a much better report of the same. So that's the reason we have done the prediction of this model on the testing data using the predict. So we got the vector of the predicted values. Now I can very well do a table or I can do a cross table, whatever it is. So let me do a simple table. So where I am having my predicted values first. So my rows will be showing the predicted values P1 and the actual values will be there as a part of the testing data $default. So I'll get my table. First on the x-axis I have my predicted, and the on the rows I have my predicted, on the columns I have my actuals. So this is what is the proportion. So it's saying 175 are correctly classified as no, 27 are correctly classified as yes, but in case of this 63 I have predicted as no, my model has predicted as no, whereas they have actually defaulted. So 63 is the error, and similarly this 35 is also error because my model has predicted as S, whereas in reality they did not default. So the overall error rate of the model, if I am looking at, it is 63 plus 35, 98 out of 300. So the error rate of the model is approximately 32.66% going with this process. Right? So the accuracy of the model is only 175 plus 27, 202 out of 300 is the actual accuracy of the model, which is around 67.33% itself. So you could clearly see there it was an accuracy of 90% when we have tested it on the training data, but when we have looked at it on a testing data, the accuracy has fallen quite drastically. The model's performance has completely worsened. But on the other side, you could see if I did not use any of the parameters to build the model also, I would have got an error rate of 30 out of 300. The 90 out of 300. There were 90 errors. So 30% was my error rate, 70% was my accuracy. If all of them I had classified as no, or still 210 would have been correctly classified, only 90 of them would have been errors, so my accuracy would have been 70% even without doing a model building process. So that is where I have to really be worrying about. So if no parameter is used, the accuracy is 70%, but after I have built this model, the accuracy became 67%. Now, which means this model is not suitable for doing the modeling for this data. So this data, I mean, all these factors that, all these variables that I have really assessed that they will have an impact on the model. I could not see that any of these variables are really impacting whether a person will default or not. Because through blindness itself, if I am able to do the allocation, still I am able to improvise on the overall stuff. And I could see here my misclassification, especially with respect to this. Earlier here this number was 90 because I have classified all of them as no's, right? So means 90 people I have classified as no, but they have actually defaulted. So it's a big loss to the bank. 90 of them have given the loans, but they have defaulted. Whereas here, such kind of category only 63 is there. So that way I can still feel comfortable that this error is reduced by doing the classification. Anyhow, these 35 people I would not have even given a loan because they are anyhow coming out as S as a part of my prediction process. So my objective may be out of these two errors, instead of just looking at them with equal importance, I may want to reduce this error quite drastically compared to this error. In that case, I should better introduce the costs involved associated with each of the errors so that the overall performance of the model can still be improved. Probably those errors I want to reduce even more further from 63. Now, the boosting, anyhow, we have taken care of. The accuracy of the decision trees. So, when I'm using the adaptive boosting, here we have set the trials as 25. So, by using different subsets of the variables, this 25 different kinds of trials are being performed, and based on the voting process, right? Which trial has voted for default or non-default for a particular training data. So the testing data 1 or training data 1, how many trials have voted for default and how many of them have voted for non-default. So based on the majority, the class would be typically identified for the training data 1. The second row, third row, 700th row, all of them will be allotted in this typical way. That is called adaptive boosting. So it's basically like if there are so many weak performing learners, so instead of going with one single learning mechanism, I'm looking at 25 different learning mechanisms. Let's say if all 25 are weak learners, I'm teaming them together. So the output of those 25 together is much better than any one of the learnings separately. That is the typical fundamental behind the boosting process. So if I am creating 25 different trials, it means like I am doing 25 different ways of learning from the data. And the combined learning has been taken up so that the combined learning is always better than any individualized learning. So it's a combination of several learners, all of them complementing their strengths and weaknesses, so the overall classification is improved. That's the typical intention of doing any kind of a boosting on any kind of algorithm. In C 5.0, that can be accomplished through a trials. Trials is the parameter that we are using in the C 5.0 formula, which will talk about how many separate decision trees to be used for the boosting process. So if there is no improvement, it will stop after a certain point. But I can very well see you can go up to 25 different trees so that the overall process can be boosted. So we can go with different combinations of the decision trees. We can change the numbers, and based on that we can still go ahead and see if our overall prediction of the test data is getting improved in any of the cases. Now, if the building of the decision tree itself takes a good computation time, more and more trees, I am asking it to build 25 different trees. So if one tree itself takes a lot amount of time to build, then probably if it has to build 25 or 100 different trees, it becomes intentional computation time, and because of which the computational impracticality can very well happen. So that's one limitation that I need to be very aware of. If the training data itself is very noisy, very random, not too much of relation, just like the current data, there is no relationship between the default versus the non-default and the various parameters that are various variables that are impacting the default. When such kind of thing is not existing, even if you add 25 trees or 250 trees, the result may not be anywhere improving. So while using boosting is still a good mechanism to improvise the accuracy part, we have to be aware of the limitations as well. It's not a magic mantra that the accuracy will directly keep increasing. So we have to be aware of the limitations as well before we go ahead implementing the boosting as a part of our algorithm. And in some cases, I can very well think of a process where I can make some of the mistakes more costly than the others, right? So I want to reduce the number of false negatives. I have predicted that they will not default, whereas they have actually defaulted. So my decision was negative, but in reality it was positive. So I want to reduce that kind of an error. So it is in this stage I can very well bring in the costs as a part of my model. So we are adding we are creating a kind of a penalty to different kinds of errors. So let's say for the same, I want my errors as 0310 or 0410. So which means if it is negative, so no yes, no yes. So if both of them are correct, if the prediction is correct, no error. Here also if the prediction is correct, no error. But if I am predicting no, but in reality it's an S, the error is very high. So it's very costly for me. I don't want this number to be much higher compared to this one where the cost is only 1. So that way while building the model, I can build it in this way so that my intention is to reduce these numbers even if it can increase these numbers to some extent. So this is what we are specifying as a part of the cost matrix, where I am specifying how many times more costly one error is with respect to the other. So this error is 4 times more costly compared to this particular error. So I really need to have an understanding regarding what is the cost associated with each of these errors, so that the overall intention is to minimize the overall cost that is associated with the error. So while building the model itself, let me bring out my model again. So this is the model. So the same model, we will put costs is equal to, the costs have to be provided in the form of a matrix. So I'll be giving it as a matrix C 0 1 4 0 and n row equal to 2. Number of rows of this particular matrix is equal to 2. So I'm giving this as an input, which is like my error matrix. So the error costs are given like this, and I'm building the model. Okay, so this is how I have built the model. Now again I can go ahead in terms of testing the model. So I'll do a P1, which I'm doing the prediction of the model. So the model is predicted now. Then again I'll create a table to see the performance of the model. So table P1 testing data. Now I could see in this case the number has come down. Okay, no and S. So this number has to come down drastically, but it has come down to this one. So the overall accuracy of the model now is the overall error rate is 91, whereas this value has come down drastically from 35 to 11. Now if I do it the other way, so if I set it as 0410, now again go ahead in terms of predicting and go ahead in terms of creating the table. Now this time we are getting a completely different set. So this number is coming out to be overall 0. So we could actually play around. This is actually increasing. So we have to reduce it even more further. So let me set this matrix itself to 1, 3. Okay, in this case it is coming down to 75. So I would like to set it in some kind of a manner where the overall thing is coming down quite drastically, and based on that the number of false negatives are coming down quite drastically while I am building mine. So this is one more way in which I can try to improvise my model by understanding what is the cost associated with each of these errors, so that I can do a better judgment in terms of a classification, and my actual data can also, and my production data can also be classified more and more appropriately. So this is what I really wanted to look at as a part of my session on decision trees. So these are the various areas I think we have covered in more and more detail. I hope you got a good amount of understanding on the usage of the decision trees and using C5.0 algorithm for classification purpose. If you have any further queries, feel free to get in touch with me by giving me a call on the number that I have provided below, or you can even send in an email at the email address that I have given there. Thanks a lot for listening to this session. Thank you very much.